I'm Bruce Torrence. I'm a professor of mathematics at a small liberal arts college in Virginia, Randolph-Macon College. And I'm here this morning to talk about my adventure over the past 4 years. I'm in my 5th year now of editing a math magazine called Math Horizons. And I don't know if how many of you are familiar with Math Horizons. I'll assume some of you aren't. It's a publication of the Mathematical Association of America. This is going to be the cover of our November issue, which comes out in about a week. And you can see it features Museum of Mathematics on the cover, which is opening next month, and the Mathematica designed logo, which you heard about, is right there. Math Horizons is a quarterly. It's intended for an undergraduate audience, and its purpose is to explain and explore mathematics beyond the classroom and show all the, talk about the culture of mathematics, the history of mathematics. So some of the things you're likely to see in Math Horizons are cutting-edge research theorems like this. I'm being facetious. Or work by the best work of some famous mathematicians. I put this up just to show that we occasionally use Photoshop. If you're really clever, you'll probably be able to see that we did a little Photoshop work there on Hardy and Littlewood. Not just Mathematica, although what I want to talk about today is what the role Mathematica plays in some of our production. We interview famous people like Randall Munroe, the author of XKCD, and occasionally people like Stephen Wolfram. This ran back in 2009. And this is coming up in our upcoming issue. The fellow in black in the center there is Bill Thurston, who just passed away in August of this year, a famous and incredibly talented mathematician. But not so well known is that he, in 2010, appeared on the Paris Fashion Week on the runway. He helped Dai Fujiwara there in blue on the left design a series of, well, clothing of sorts. So you can read about that in the upcoming issue. But I show this page, first off, because I really like the way it came out. I think it's a beautiful page. But also want to point out that Math Horizons is unique among mathematics publications in the sense that it's full color on every page. And that just happened a few months before we took over as editors. I'm a co-editor of this. And coming from a mathematics classroom background, it was quite an experience stepping into this role and having to fill pages with color when your stock and trade is working in mathematics. So for example, in the upcoming issue, this was a page as it came back from our designer, and it just to my eye wasn't quite colorful enough, and the final page we ended up going with looks like this. And you can see this beautiful illustration right here. I just wanted to put something on the page. We had a little space, and having Mathematica and an experience with Mathematica and being able to use it is just invaluable for situations like this. This is literally a one-liner. Just going to knot data, and I shopped around for a few knots. I liked this one, and then just changed the lighting a little bit to match the fonts and or match the colors, the designer had come up with. And that's literally it. This took about 10 minutes while watching the news, and exported that as a JPEG, popped it off to our designer, and the round 2 page proofs came back, and I think looked much, much better. And this sort of thing happens all the time. This is just, I'll show you a few quick pages here of illustrations that were made in Mathematica that I went to some effort to sort of hide that here, trying to make them not look like the stock Mathematica images. But it's very, very easy to do that, and it's maybe easy to forget that Mathematica is a tool that is just really, really simple to use to produce really beautiful graphics if you put just a little bit of effort into their presentation. I did import a little JPEG image of a glove there, but other than that, that was completely made in Mathematica. So every issue is just full of stuff like this, so I don't want to bore you with all that, but I'll show you some what I think are more interesting applications. This was an illustration that appeared in February of this year, and this article was about, it's an age-old problem, a variation of an age-old problem where you drop a few lines at random onto a plane and ask yourself how many regions can you divide the plane into with this small set of lines. And the authors here were saying, what if we take the plane and wrap it into a surface like a torus, how many regions will the torus be divided into? So the authors were, I made this graphic because they didn't really know how to make a graphic showing how, what would happen in a 3D space, and they were kind of amazed I was able to do it. And this was really, really easy. It's just a parametric plot of a torus, and Mathematica supports this whole texture wrapping. So you can just take any image you want to and wrap it parametrically around any surface, and it's very, very easy. In fact, the hard part was actually coming up with the the actual. Well, this was easy. This was the line pattern that they wanted to use for this particular thing. But coloring the lines, coloring the regions would be a little bit tedious if you had to specify the vertices of all the intersections of the various lines. So what I actually did, just to save time, was to export it to Photoshop and use the paint bucket tool and fill in the regions, re-import it, and use that for the wrapping. So it actually took longer to make this image than it did to wrap it into the torus. Here's another page from that same article. So Mathematica was used extensively for every one of these illustrations. The authors provided me with illustrations, but very often they're just not quite up to print standard, and we need to do a lot of work. And Mathematica is the go-to tool for that. And very often we experiment with things, and I'll show you. This was our original conception for an image for this article. Was the article opened with an analogy with pizza, saying how can you slice it? How many pieces of pizza will you get if you just arbitrarily make a few slices in it? So we thought, oh, and they're going to wrap it around surfaces. So I said, oh, let's wrap a pizza around a surface. And oops, sorry. And then we can just take this and make an equirectangular projection of it like so, and use that for the wrapping on just a parametric expression for a sphere. It's all pretty simple, and you get this absolutely disgusting pizza ball. So we decided not to use that. It's kind of cool, but yeah. But this whole idea of wrapping images around spheres came out in a story we ran in 2011. This was the cover. And there's a whole school of photographers now that are making panoramic images. You can make a panorama with an iPhone now really, really easily. But take that idea to its extreme, and you can keep the camera fixed at one point and take images in every possible direction and stitch them all together. And what you really have is a spherical image when you're done, although it's hard to print a spherical image. But you could then take that spherical image and, say, project it stereographically, or use any map projection you like, and get a nice flat image. And this is a stereographic projection of a panorama that a photographer made in Paris, which is really, really nice. So we did an article about this. In fact, I co-authored it with a guy named Dave Swart. I was trying to get someone to write it, and we couldn't find anyone who was willing to do it, but Dave said he'd team up with me. But this little picture right here I want to call your attention to. This was, the whole school of photographers doing it. There's several dozen, I think, worldwide who are really, really good at it. I've never seen an illustration showing conceptually how the idea works, how you can take make it the spherical panorama and then project it stereographically. And Mathematica is a perfect tool for this. So for instance, this is an image by one such photographer, Sebastian Perez Duarte. It's an upside down equirectangular version of one of these panoramas. Then we can the equirectangular is very easy to wrap around a ball like this. And in the Mathematica, of course, you can grab this thing and you can actually imagine what it would be like to stand in this place. You're standing outside the ball looking in, and ideally you'd be inside the ball looking out. It would look just like the real world. But then use image transformation. You can make the stereographic projection. This is a low-res version just because it's all we needed, but the same illustration that appeared on that page. And finally, you can use this, embed this onto a polygon in 3-space, and then superimpose the ball with the projection, and you get a real sense of how stereographic projection would work on a sphere with an image painted on it. And we, of course, just had a very small flat image in the article, but the Mathematica is perfect for making this, and it really is just a handful of very simple coding to make that work. So just a great tool for this sort of thing. Mathematica has made it onto the cover of Math Horizons on a number of occasions. This was from an article written by Stan Wagon and Mark McClure who are both here at the conference, I believe, called Four Coloring the U.S. Counties. And, map coloring, the four-color theorem. It's possible to four-color all the states in the U.S. People have done that. But I don't think it had ever been done county by on a county-by-county basis. And finding an algorithm that would actually produce the coloring like this was the topic of the article. And
interject one point.
Please.
In making that diagram, we learned which county in the U.S. was the most friendly. In other words, which one has more neighbors than any other county. There's one that's a clear winner. And I wrote to the county government saying,
you should.
you're the friendliest county in the United States. I never got a response.
How friendly? Yeah, that's not very friendly.
I don't know. It's very hard to guess which this would be, and I don't think anyone had ever observed that before. So that was nice. The only thing was
interesting. Yeah.
It's Washoe County in Nevada, the county that contains Reno. It may be that vertical red one there. No, the vertical blue one, just down the left from the vertical red. That's it.
Vertical blue. So where are we? Right here?
Higher, left.
Right there.
Left.
Oh, well, this look at that. Yeah, okay. Yeah.
13.
Now, this work was done in Mathematica, which made my job very, very easy. I could just open up the Mathematica notebook. Here was the four coloring. Here is the underlying graph showing the connectivity, or the adjacency. And then just zooming in on a superimposition of those two things, I really started liking the abstraction, and I thought it was a really nice idea for a cover, just because you can see just enough structure here that it looks, you can see Kentucky and Tennessee, but it's still abstract enough that it really makes you ask questions, and then it makes you want to open the magazine, which is the point. But again, once you have those images, this is just it's very quick. It's just a matter of figuring out what a nice sized crop would do. And I experimented with several. Another cover that I really liked was this one. This was in April of 2011, I believe. And this is an example of a nowhere neat tiling of a square. It's a 35 by 35 square. And these are all just found math images. The MBA likes to have these photographs that have mathematical content and the mathematical themes. And here's a picture of the underlying structure there. So there's, I think, 53 individual squares if you count them all up. Each one has, most of them have unique photographs in them. The ones that are colored green and yellow and red and dark blue, I think, are repeated because they've got too small to put unique images in. And of course we had to give image credits. That was what took forever with this, and getting permissions and such. But Mathematica was used to actually do the perfect square cropping, put a little black border around each image, and then used image compose in a nested fashion 53 times to gradually build this and place every image precisely in the right location to show this nowhere neat tiling of a square by squares. So it's just sort of a fun thing that didn't have anything to do with a particular article, but the overall effect, I think, is quite nice, and Mathematica was a perfect tool to do that. We use Mathematica in a number of other ways too. This is just a spread of an article by Joel Cohen. He had seen a picture of a piece of art. It illustrated the Pythagorean theorem, and he wondered if they had oriented the picture differently, if the artist could have used a little bit less copper, a different wrapping, so to speak, of the theorem. And I was left to illustrate these, and I went ahead as the illustrations were taking shape. I said, well, what's the best if A and B are the side lengths of the two sides of the right triangle? What are the best values of A and B to sort of make the reader wonder which is better? For certain values, it's obvious that one takes a lot more copper than the other. So I ended up actually settling on a 5, 12, 13 triangle. But and just to show you, I don't want to emphasize this because it's really, really arcane or just simple but this is what we end up doing typically for an illustration. We have to make sure the fonts are right and the individual font sizes are right. So there's a lot of little, the code ends up, a very simple code ends up being a little longer than we'd like to see. And working with these braces it can be a challenge, but Another case where we had sort of a dynamic interface tool was this page. We used a Voronoi diagram to set up the background. It's just a bunch of limericks and so here we could experiment with different page layouts really easily, and change the colors and experiment with different just built-in color schemes. It was very simple way to experiment, and then just paste a snapshot of it once you like it, and use that as the background for the page. So a great production tool. Another case like this, we have a diagram showing this article about a student who wanted to use Bezier curves to write a love letter on a calculator to another student. I mean, really silly article, but just showing how cubic Bezier curves work and producing these three pictures. The ones he sent were done on a calculator and they looked awful. So I redid them, and just label placement was just an issue. So I built this little tool where I could individually move the placement of the labels, and then just paste the snapshots as I needed them. So I could make one image to the next very simply, and so doing things like this happens all the time. I'm showing you just a few quick examples, but it's really useful for the types of things we do. Mathematica is used in somewhat deeper ways as well. This was an article that we did several years ago on storytelling numbers by Tanya Kovanova. An autobiographical number is a number like this one, where the digits tell the story of the number. That is, this number has 1 0, 2 1s, 1 2, and 0 3s. So it tells you how many digits it has just by reading its digits. And the article goes on to explore variations on this theme. In particular, you can start with a number like 1 2 3 4 and say, well, that number's got 0 1s, 1 1, 1 2, 1 3, and 1 4. So there's the biography of the number 1 2 3 4. And then you can take the biography of that number. That has 1 0 and 4 1s. And the next, the biography of 14 would be 0 1s, 1 1, 0 0, 0 0s, 1 1, 0 2, 0 3, 1 4, and so forth. And you could build these chains, and the question that she addressed was what happens in these chains. And they all deteriorate to a loop that either begins in 2 2 or I think 1 2. But this was a case where I wanted to check her mathematics, and in doing that, you just said, well, let's just automate this process. It's pretty simple coding, so that we can see, for example, the number 1 2 3 4. That's just the digits of the number 1 2 3 4. Here's the chain of biographies that result, and here's it does one iteration of the loop at the end. But you could take any number you want and see how it goes. And by looking at lots and lots of these, I decided which ones I wanted to use for the illustration. And I was quite pleased in the end. We were really tight on space in this issue, and I wanted to put some color on the page. So I was able to squeeze a little figure like this in with a little figure caption right into the body of the text and wrap the text around it. So it took up hardly any space at all, but provided a nice little thing. And of course, the figure was made in Mathematica too. That's just a graph plot, I believe. This was a few years ago, so some of those commands have changed a bit. Let's see. Oh, another one was a puzzle a fellow had submitted. I think I showed the page with the solution of this puzzle. But these puzzles, you start with a rectangular, an empty grid, and you want to put a digit from 1 to 9 in each of the 36 spaces. And what you're given as clues are what the column totals are. They're given on the top there, what the row totals are, what the diagonals are in this direction, what the diagonal totals are in this direction, and what these off diagonals, these second diagonal totals are in each direction. So it kind of is sort of the same process that a CAT scan or an MRI would go through in building layer upon layer of images. You're looking through, and you can see what the total density is, if you like, in several different directions. And from that, you want to try to fill in the details and try to figure out what each individual number is. And the author provided a solution to the puzzle, and I wasn't sure if it was unique, so I just said, well, let's just check this, and call the 36 positions x11 through x66, and come up with a bunch of constraints showing what the row sums are, the column sums are, the diagonal sums, and so forth. It takes a little bit of typing, but not a whole lot. The constraints are that they're integers ranging from 1 to 9. I made a table of those and joined them all together and said that's the clues. And I just listed all the clues just so I could see them all in one place. And just used reduce. Said reduce this over the integers, and it gave me a big OR, a big result with the head OR, and applied list to it, so it was a list rather than a logical statement. And said, how long is it? Well, it's 19,000. So no, there was not a unique solution. There's many solutions to that. But the author was very surprised by that. There were so many solutions. So there are dozens and dozens more examples. Pictures. I actually drew these pictures in Mathematica rather than Illustrator would be a perfect tool for something like this. But once you draw a figure in Mathematica, it's really simple to do this, and then you can make it make a perfect circle and so forth very, very easily. This was one on mathematics of dancing and dance moves. So I built a little Mr. Roboto in Mathematica, and once I built him, it was very easy to rotate him and reflect him and show that a glide reflection is a composition of a reflection with a rotation, which is the purpose of the illustration. And there's a number of electronic supplements that we've done for, and this is, I think, an area that, as the magazine, I've only got 1 year of editor left, but certainly we're already discussions about moving toward an electronic iPad, version, an e-reader edition, and how would that look and how would that work, and what are the possibilities for illustrating mathematical ideas. And of course, CDF is a really rich possibility, but even now we have demonstrations that you can download from the site. Some of these are on the demonstration site. All of them are on the Math Horizons site. This was just an article that illustrated that what's the age-old question: should you run, or how fast should you go when you're walking through the rain to stay as dry as you can? And the classic answer is it's a limerick, isn't it? When caught in the rain without Mac, run as fast as the wind at your back. And I forget how the rest goes. But the optimal speed is the speed of the tailwind, if there is a tailwind, if you're a rectangular solid. But we found if you're an ellipsoid, you should actually go faster than that. And since people are a little more like ellipsoids than rectangular solids, the whole convention there is odd. But you can see exactly how the effect changes, and the optimal speed is in green there at the bottom. The Burt pancake problem. This was an article on bacterial computing. Bill Gates' contribution to the academic literature was working on the burnt pancake problem, I believe, as an undergraduate at Harvard, where you have a stack of pancakes and you have two spatulas, and you put the first spatula in the stack and lift up the top ones, and put the second spatula somewhere in the stack and flip over the rest, and then put the original top portion of the stack back. And how many flips would it take to put the pancakes in order from largest to smallest? So you can set the flip zone here where the spatulas are and flip these things over and try to solve the puzzle and put them in order. And pancakes can be burnt on one side. The idea was if the pancakes are burnt on one side, the waiter wants to flip them all so that they're the burnt side's down so the customer doesn't notice. But they actually programmed bacteria to solve this problem in a lab, and that was the point of the article. I've got one more. You know what? I'm going to even leave that one off because we're running out of time. I've got a couple minutes for questions if anyone has any.